well, actually, also my welcome to you all. Thanks for being here. And yeah, this talk is going to have some non-zero overlap with my talk in Rome and my talk in Leipzig, but there will be new content, so you don't have to leave the room if you have heard me before. All right, so this is the outline of the talk. For some of you, the first part is probably just a bit too obvious, but I'm going to say something anyway for those of you who haven't heard that much of a QFT yet. And then I will spend some time talking about quantum reference frames, which maybe is a bit less familiar subject. Okay, well, algebraic quantum field theory, but if you haven't heard this before, which is very unlikely, but hey, you know, it happens. This is a framework to understand mathematical structure of QFT. And the idea goes back to Haag and Kastler in the 60s. So they were trying to formalize QFT on Minkowski spacetime. And the idea is to, well, encode all the physical information in assigning operator algebras, C-star algebras, or von Neumann algebras to regions of spacetime. So you have a bounded region of spacetime, and then you assign to it a space of observables that you can measure in that region, and this is modeled as some operator algebra. And then when you have the inclusion of regions, that also induces an inclusion of algebras, and then you get the structure of a net. All right, and then there are some axioms that one requires that correspond to physics, and one of them, the very important one, is causality. So you have, if you have two regions of spacetime which are space-like separated, so there is no causal curve that can connect these regions. We are talking about Lorentzian geometry here. Then the corresponding operators in these regions should commute. So there's sort of independence of measurements that you can well perform in these regions. And then there is the time slice axiom, which has something to do with time evolution. So it's a quantum analog of the initial value problem. If you know the operators in the neighborhood of a Cauchy surface, so you know the A of n, which is a neighborhood of some Cauchy surface, then you know the operators in the whole region whose Cauchy surface this is. Hence, well, this is a stronger condition than the one given before. So A of n, by definition of the net, should be contained in A of O. But if n is a neighborhood of a Cauchy surface, then A of n is equal to A of O. All right. There are more axioms, but these are the axioms that are relevant to this particular context. So I'm going to stop here with the list of axioms. And then, well, things went beyond Minkowski spacetime. And nowadays we study QFTs in this framework on more general spacetimes. So we, well, in a sense, we include the effects of gravity, but not quantum gravity. So just classical gravity. So we study QFTs on, well, some other physically relevant spacetimes. There are solutions to Einstein's equations. And the sort of prominent and interesting examples are black hole spacetimes, for example, Schwarzschild, or cosmological spacetime, Friedmann, Lamette, Robertson, Walker, De Sitter, and, well, you can think of more examples, some combinations of the two. And again, here the idea is the same. So you assign algebras to regions of M, and, well, in this case, relatively compact regions. And again, Einstein causality and time slice axioms generalize to this context. And finally, if you want to generalize things a bit further and go more abstract, you can formulate this in terms of giving a functor on some category of spacetimes to some category of algebras, but I'm not going to talk about this aspect today. And well, I mean, there's a locality in the title, local algebras, and people often call this approach local quantum physics. That's, of course, the title of the book of Rudolf Haag, which is one of the foundational texts in this community. But what does it actually mean? And the word locality is used in many different contexts. So I want to maybe stop for a second and ponder upon it. So first of all, I mean, sometimes in physics, when people talk about locality, they actually mean localization, so that the observables should be localized in bounded regions, or like more formally, that fields should be point-like objects. Okay, so that is true in some cases, but it's not always the case, even in quantum field theory. And then another sense in which people talk about locality is in terms of the interaction. The interaction in QFT is local, which is actually an important aspect. But, well, again, you can imagine, you don't even have to imagine, you can construct interactions which are not local and still give you something that you can treat in terms of the same QFT methods. And also, I mean, in this more abstract framework, obviously, sometimes you have theories that don't come from a Lagrangian, from interaction in an obvious way, or not at all. So this is not so easily applicable in our framework. And finally, there is locality as causality, which is this commutation at space-like distance. And when I talk about locality, I will try to make it clear which one of the notions. It's usually the first one or the third one, but the third one I will try to call causality because I think that it's good to distinguish these things. Because the first time, it's actually not very good thing to expect, because we know that this is broken in very sort of physical models that we want to be able to describe, for example, QED. So if you try to, make sense of QED in a rigorous way, well, first thing you notice is that there is no such thing as point-like electron. And well, I mean, I don't know what's your background in physics, but there is one thing that we know classically about QED, which is relevant here, is Gauss's law, which means that if you have a charge and then you take a integral of the flux around any sphere, any surface that encompasses that charge, then the value of that integral will tell you about the value of the charge inside. So it doesn't matter how far away you go from your electron or some configuration of charges, you will always know it's there. So the type of localization we are talking about here cannot be just a pointless localization. You cannot put an electron in a box and forget about it. Yes.
But I mean that is solved by noticing that the electron is not a field in your. It's not an observable in your theory. So the observable is the Wilson line.
Exactly.
And the Wilson line satisfies the first part.
You are absolutely correct. Yes, you stole my punchline. Indeed. So electrons are actually stringed or cone localized objects, and that's why I'm making this little excursion, because they are not point-like localized, but they are string localized, and yet they obey the causality relation. So that's perfectly fine. So we do expect observables to have some more interesting types of localization. And yes, the thing that people use is either a Wilson line or a Dirac string, or however you want to call it. Thank you for that. Okay, so however, things can go bad if the observable you're looking at is localized everywhere. Because if it's, I mean, for a given value of bad, but if it's localized everywhere, then you cannot really talk about commutation at space-like distance, because everywhere is, everywhere. So, for example, if you are taking quantum gravity seriously, and the fact that we should expect diffeomorphism invariance, then you expect that, well, in quantum gravity, at some point, this you won't be able to talk about Einstein causality, even in some sort of perturbative way, because the localization is just too huge. So here one uses the concept of relational observables, and this is not very new. I mean, these were used in various approaches to quantum gravity for decades, and there are people in loop quantum gravity which are using these things a lot. But yeah, so there are also, methods in perturbative AQFT to treat such observables. And I mean, the key idea here is that you describe relations between local quantities, okay? But there is something intermediate. So before we go all the way to quantum gravity, which is difficult somehow and a bit messy, and there are other problems there, I think it makes sense to look at some sort of intermediate situation. So when we go away from standard notions of locality, we are not in quantum gravity yet, but we are in a situation where studying relational observables, relational concepts makes sense. Okay, and this situation arises, for example, if we study systems where there is on the spacetime which has a large isometry group, and we are looking for the space of invariance under the action of that symmetry group. Okay, and this concept of relational, or actually in that context, relativized observables, it's a sort of intermediate situation that I would like to talk about here. And to construct such relativized observables, one introduces quantum reference frames. So quantum reference frames, I will talk about it at length, but this will be sort of a reference system that will be coupled, will be interacting with your, say, local net of algebras, and then the observables we are going to look at some joint observables of that system as reference frame. So this is going to be the main subject of my talk. And these observables that arise this way, they are not local in the sort of traditional sense. They are, well, not the full relational observables in quantum gravity. They are something in between, and we call them semi-local observables. So when you see that name, it's probably either me or Dan or Chris, one of our friends involved in this. So yeah, playing with these things these days. Okay, right. So before we get to the observables, I need to spend one slide on measurement. And this is one of the aspects of QFT that should have been studied long ago, but hasn't. And thanks to my dear colleagues, Chris and Rainer, who are now in the back of the room, this problem has been addressed finally in 2020. And Chris is going to tell you all about it tomorrow. So I'm going to postpone detailed discussion and all the questions to the talk of Chris. But I will need just like a little cartoon so that you know what I'm after in this particular context. So what do I mean by measurement and by measurement scheme? And this is obviously outrageously stolen from Chris and Rainer. So this is none of my idea, but I think it's a very pretty idea. And we are, QFT people, so we really want to talk about measurement of QFTs. Hence, it does make sense to think about this whole measurement process as something that occurs where both the system and the probe are quantum field theories. Okay, so we have a system, net of algebras A, and we couple it to some probe, net of algebras B, and this coupling occurs in the compact coupling zone K. So that is actually important for discussion in this talk. And then, well, we have some states for both of these theories. So we have the probe field prepared in some initial state here in this blue region. Well, this region, if you don't distinguish colors, which is uncorrelated to A in there. Sorry, that still requires some practice from me. And then we measure some probe observables in the post-coupling region, which is the one here. So it captures what the basic idea of measurement, I prepare early and measure late. And then, well, what we measure here, so the expectation value of B corresponds to the expectation value of some induced system observable, which is localized in a region containing this K. So we read off the information about the system from what we can measure about the probe, which I think is very simple. Okay, so Chris will tell you all about the details of this scheme, and we think of this setup as the measurement of A. Okay, so what is important here is that, well, this story somehow depends in a non-trivial way on the choice of that region, on where this coupling happens, okay? Where and when, because we are talking space-time. So let's say that we have a background with some symmetry group, and that both our quantum field theories are covariant under this symmetry. That's not unusual to expect. But this coupling zone K, well, this will move when I apply that isometry. So here is the picture. So we have the coupling. We act on this by this symmetry G, and then we have a new coupling region. So we move our experimental setup somewhere else and sometime else, and then we perform the measurement, okay? So in this way, so we transform K, we can transform A and B as well. So in this way, we actually have a way to act with this G on this induced system observable that we measure. So in a way, we act with the symmetry group also on our measurement scheme. So instead of having just one measurement scheme, now we have a whole orbit thereof under the action of this symmetry group, okay? But in the end, we want to actually know what we measured, when and where, okay? So it is actually relevant to have the information about the localization of K, but that won't come from the system or the probe. That has to come from somewhere else. So in practice, of course, where you measured things, right? I mean, otherwise you wouldn't find your experimental setup. So you find your institute on the map, and then you find the right room in the building. That's not a problem. Also, your watch tells you exactly when you're measuring, and so that you are not late for your measurement to start. But these things are actually secretly an external input. So they are, the way I described it, classical systems that allow us to measure distance and measure time. So in classical mechanics, we call that a reference frame. So we have to fix a reference frame. We have to fix a clock and origin and 3 unit vectors that describe directions. But of course, in quantum theory, well, these would all be quantum, right? Because the world is really actually, if you take it seriously, quantum. Okay, so that idea of telling people where and when the measurement happens is actually somehow, in a way we forget about it because our classical intuition is kind of, skimming over it. But if we are taking quantumness seriously, then this will actually be something non-trivial. Okay. So before I go there, there's a small interlude because, well, you might ask, what if my spacetime doesn't have symmetries, right? Then I don't have a problem. Then why are we talking about this? But then I think one has to maybe take a step back and think about, well, again, quantum gravity or even classical gravity. Okay, so if you remember your GR course, and if you never took a GR course, if you remember talking to a friend who took a GR course, you would know that in manifolds, I mean, manifolds are great mathematical objects, but points in manifolds don't actually have a physical meaning in GR. So they are just labels, but they are not really physical quantities. So from that viewpoint, this specification of a coupling zone, the way we said, oh, this is K, it's a subset of a manifold, this is this K, that actually doesn't have a physical meaning. Okay, so we use some arbitrary set of labels that in practice would have to correspond to another physical system the way I just described. And this sort of, so here, the kind of symmetry that we are talking about is full diffeomorphism symmetry. Now, if we consider a spacetime with symmetries, the background is itself symmetric, and instead of doing that large, diffeomorphism invariance, we reduce that to something much smaller, which is the isometry group. But this is still kind of the same general issue that the points in manifolds don't have physical meaning. Okay, so well, at the end of the day, one day, if we are going to go back to the problem of observables in quantum gravity, then we will probably have to come back to this problem. Okay, so and as I said, if we are being serious about the quantumness, then this reference frame also has to be quantum. And then the observables we are talking about would be combined observable algebra of the system and the reference frame. Okay, so here we have some A that characterizes the system. Here we have AS, we have AR that characterizes the reference frame, and we are taking the space of invariance. So mathematically, this is the object we study. And now, well, I guess the first part of that object was already kind of explained using the Hack-Kassler framework, but now the second part of this object needs a word of comment. Because, you can talk about quantum reference frame, a lot, and about there's a lot done actually in the quantum information community. But at the end of the day, you want some concrete mathematical definition. And well, the one that I'm going to use is due to Karol Głowacki and Lavridge, proposed in 2023. And this is specifically a quantum reference frame with some action of symmetry group on it. And here, for now, I'm going to say sufficiently nice group G. In particular, I mean locally compact. So the quantum reference frame is a triple. So we specify a Hilbert space. We specify a positive operator valued measure, so P of M. So this is given as a map from Borel sets of some homogeneous space sigma, which arises as a quotient of my symmetry group G, which is the one that, well, this is the underlying symmetry of the quantum reference frame that we are trying to describe via by some subgroup, closed subgroup H. Okay, so sigma arises this way, and we think of it as a space of labels that this quantum reference frame offers. And then the P of M is a map from Borel sets of that to bounded operators on our Hilbert space. Okay, and we have also a strongly continuous unitary representation of G on this Hilbert space. And then there is a consistency condition between how G is acting on, well, essentially on sigma, and in particular on Borel sets there, and how this unitary representation of G induces an action on operators in B of H. Okay, so this is the very simple consistency condition, and that's it. So that's a quantum reference frame. And well, we are going to look for things that smell this way. Here is an example, and I think, well, I mentioned this example in several of my previous talks, so people who have seen it before, I think already know what's happening. But yeah, it's a particle on a line. So you have a Hilbert space, which is just L2 of R. The symmetry is translations. And then here, I mean, you have the obvious, well, representation of translations using the momentum operator. And you have the obvious action of translations on intervals just by shifting. And then this condition, this consistency condition between these actions, it turns out is actually equivalent to the permutation relation between the position and momentum. So that is a good sanity check that this notion of quantum reference frame actually gives us what we expect for a particle on the line. Okay, so here is a bit more complicated example. And this is actually then, well, more directly related to something I want to talk about later. So is this notion of sharp and unsharp QRFs and observables. So it's related to the problem in quantum mechanics, quantum information theory of time, measuring time and thinking of time as some sort of observable. And it doesn't really go directly, but well, so here's construction, the kind of sort of blueprint for what I'm going to do later. So if we start with a QRF, so all these data, and then yeah, we can choose a projection, and well, so ideally we would like to think of this representation of time translation as given by some sort of a Hamiltonian, but the problem is that well, this wouldn't be bounded from below, so that leads to trouble. But we can choose arbitrarily a projection to, for example, positive frequency representation, or to something else which is bounded below. And we obtain a different quantum reference frame using that projection, which I will refer to as compressed quantum reference frame. And then H is semi-bounded from below, so that's so much better. And then this can be used for defining a generalized time observable. So people, I think, thought about things of that sort before, like time of arrival observable. And I think this is a similar thing as Brunetti-Frenhagen, right? So that concept has been around. Yeah, right. So there is a paper of Brunetti and Frenhagen from 2002, and with physical interpretation of such things. So that's a very nice example of application of this whole business. Okay. Another well, more technical aspect that I would like to mention is the question of, well, let's say I chose a quantum reference frame, I chose an observable, I want to use it for, you know, telling us about localization of my coupling region. So what can go wrong? One thing that can definitely go wrong is that this space sigma of labels might not be fine enough to actually distinguish where my coupling zone is. Okay, so my set of labels might be inadequate for, precisely localizing the system. So yeah, so this is a bit of an abstract construction, but yeah, just to briefly explain what's going on. So yeah, as I said, we have the action of G on these measurement scheme as a whole, right? So given the measurement scheme, we can talk about the orbit thereof. So all the possible, say, translations of that measurement scheme in time. So let's think of time as the symmetry we are trying to fix. And then we can talk about the induced system observable of this this orbit, which is then defined via smearing the induced system observable for a given measurement scheme if we specify a covariant map which goes from this space of values to the space of to the orbit of the measurement scheme, and then we smear out over essentially all elements of that orbit using this map. And so this defines as the notion of a relative measured observable. And then this is, of course, invariant under this action. So alpha is the action on measurement schemes, and this is given by the joint action of the reference system. This is the action on the system, and this is the action on the reference frame algebra, which is bounded operators on HR. Okay, and then with this sort of prescription, we can talk about the algebra of observables that arise this way. And yeah, so coming back to the question of things being good enough for our purposes. So we want this parametrization, this choice of map, the choice of map here that enters the definition of our relative observables. We want to be able to find this map. And this exists only if sigma is sufficiently large, so good enough for being able to measure what we are trying to measure. So we want to be able to use these elements of sigma to label our measurement schemes. And this is essentially what that map is doing. And then the question is, can we find that covariant map? And is sigma good enough? Okay. And that condition that, sigma is large enough corresponds to the notion of compactly stabilized quantum reference frame. So here that obviously depends on the choice of H, right? So given G, then sigma is the quotient by H. So the choice of H is actually relevant to this question. And then quantum reference frame where you have sort of sufficiently good resolution is called compactly stabilized. If you read our paper, we use that term a lot, so I thought that it would be friendly to introduce it here. Okay, so now we assume that we have such compactly stabilized quantum reference frame, and we have a nice enough group G. So then there is a nice fact that we can always represent it as a standard QRF where we are using L2 of G, so square integrable functions on this large group as by Hilbert space. So this is a sort of natural choice times some extra that corresponds, well, essentially then corresponds to degrees of freedom that are killed off by taking this quotient. Then we have, again, a standard action by left translation in this group, inducing the action on L2 of G. And then this procedure to go from this standard, now sharp quantum reference frame to the arbitrary QRF, compactly stabilized QRF that we started with, is this compression by projection that I mentioned in the context of the time observable. Okay, so this is a very nice mathematical tool, and this is not new. I mean, this is proven using Mackey's imprimitivity theorem, and I don't know when was that? Do you have a date for that? When was that?
50s.
Early 50s, yeah. So when I say it's not new, it's very not new.
Was applied to sort of projection value
Yeah,
measures.
yeah.
There were variations on it in the 70s, which were applied to these PLBMs. And
But yeah, I mean, these are the tools that have been around for a long time. But I think it's nice that we're using it now for something more modern. Okay, so that was a bit more technical introduction to QRFs. What are we doing with them? So yeah, we are constructing spaces of invariants for interesting systems, okay? And what we find interesting is probably subjective, but here are some examples. So this is actually still a bit of a mystery. So there is this work I have on relational observables in perturbative quantum gravity. So aspirationally, we want to put this under the umbrella of quantum reference frames, but that's a bit of a work in progress. Now, sort of one of the relatively recent results is well, inspired by ideas of Witten and the paper of Ed Witten, Roberto, Jeff Pennington, and Chandrasekaran, where this quantum reference frame is just another quantum mechanical system, and you know, the system is just a QFT. So we can think about examples of this sort. And even more recent paper is the work of Chris, Dan, and myself, where we have a situation of QFT with boundary. So in this case, it's, well, I should maybe draw a little picture in, people can see it. So we have a situation of something we call a Cauchy lens. So these are two Cauchy surfaces kind of glued in the middle. Okay. And then we consider electromagnetism inside it, but also include the boundary and the corner into our consideration. And these, we have shown that these boundary and corner degrees of freedom can be used as a quantum reference frame for the bulk. So that was a nice little model, and we think that this is a more general phenomenon that is worth studying and maybe has bearing on things like infrared problem in QFT, which I find personally very interesting. Okay, so these are the existing examples. And yeah, as I said, this infrared problem would be generalization of this to asymptotic degrees of freedom.
Boundary conditions do you put on the corner?
Neumann boundary conditions.
Why?
Because they work.
on the corner at this point of I mean, this is a globally hyperbolic paper,
Yeah.
or at least the interior
Yeah.
is globally hyperbolic. Then you don't have to put it in boundary conditions. Put it inside a.
Yeah, so
inside a
that's
tube
more,
or-
yeah, for the
Um,
construction of the state, yeah. I mean, you can probably say more about it, yeah.
We condition that's essentially, well, don't kill off the electric flux at the boundary and things like that. There are various choices of boundaries.
Yeah.
But is the boundary physically made out of some material?
It could be.
Could be, yeah. I mean, that would be the physical sort of
Why is that?
justification.
Is that not treated as quantum as well?
Sorry,
Why is boundary not treated as quantum?
Well, it's a metal.
Yeah,
one could have some system living on the boundary and being coupled to the theory as well, and then you get some dynamical boundary conditions. These have been also studied.
yeah. Yeah.
But not.
I mean, in a sense, right? I mean, it's a bit of, well, okay. It's a toy model, but not entirely toy model. I mean, you can think about like systems in solid state physics where, you know, you have physical boundaries and you have actual, yeah, you can have like, as Dan said, dynamical boundary conditions that corresponds to some dynamics on the boundary. You can study defects and things like that. So I guess maybe, yeah, if you think about solid state examples, then this becomes slightly more physical. I mean, in this context, I think so mathematically you have the freedom to choose, right? And then what I would like to see for my own personal satisfaction is you know to see the limit with the boundary going to infinity, where this boundary becomes more of, again, yeah, sort of mathematical construct, because we cannot go outside the universe and as far as I know, and put boundary conditions there. But yeah, thank for the question. I still have 4 minutes, so in the last 4 minutes, maybe I will just say a few words about this example. I mean, I talked about this before, but let me just briefly, well, this everybody knows that, right? That observables in a QFT are von Neumann algebras, and you know, this finally is the audience where I don't have to say what a factor is. So yeah, there are von Neumann factors, and they have 3 types, and some people here were involved in classifying those. So I will skip that slide. And I have to argue why it's interesting. Right, so everybody also knows that in AQFT, you know, local algebras are of type 3, and people thought it was tragic, but it's not tragic, actually, it's great. But unless you want to compute entropy of a region, then it's less great. But we don't worry about it. Now, well, the whole talk was actually about the question whether a net is enough. And well, if you take this point of view that we are interested in these relational observables with the net and the reference frame, well, the net is not enough. So what is the type of these relational observables you get from combining the net with some quantum reference frame? So this is the question Chris and I and Dan and James and Leon asked ourselves. So how to operationally describe measurements in the presence of symmetries, and how that this affects the type of algebras you have, okay? And as I said, this was heavily inspired by this really nice paper by Chandrasekharan, Longo, Pennington, and Wheaton from 2023, with the example of translation invariant observables of a quantum field on a de Sitter static patch, okay? So here is very briefly the idea. So the observer system is just a clock. And well, I mean, this is very similar to what I already had said about unsharp time observable. This is the de Sitter spacetime, this box. A static patch is a region where observer can actually control experiment. So order the experiment to be performed and receive results. So this is this little triangle. And then you consider a quantum field in a Bunch-Davis type state. So this is a thermal KMS state of this. Obviously, we have a von Neumann algebra of the static Paschen. We have the unitary action of the time translation. Okay, and physical observables are these variants. So in our paper, well, we describe this observer, this clock as a quantum reference frame. Then we describe the measurements there using Fürst-Fech measurement scheme. And then, well, that implies that observables, this invariant relational observables, are type at most to infinity, so they have a semi-finite trace. But then there is a very interesting, in my opinion, observation that if this QRF also has some nice thermal properties, so admits a KMS weight with the same temperature as the system, which was essentially the observation of Dan, then you in fact obtain something of type 2-1. So there is a finite trace. So thermal properties actually are crucial to, in the end, get well-behaved traces. And there was a similar, well, not quite similar, but there was another paper with QRFs in mind by these wonderful people, and it's also worth having a look because then it's a alternative perspective. Okay, I think it's time to finish. I'm going to skip all the technical details. And thank you very much for your attention.
Thank you very much. Do you have any questions or comments? No.
No, but you know everything.